Hey, welcome back. This is the last chapter in calculus. And what is it about? It's about the reverse of the derivative, okay, which we're going to call the antiderivative. So an example of what the heck are we doing here? Let me get my pen ready there. You know how to go in one direction. You basically have a function of some sort, and you take its derivative. F prime of x will be 2x, right? Now we want to go in the other direction. So you're going to be given basically a derivative of something. Let's say 3x squared, and you have to figure out what was the original function that led to that, right? So, what is? Can you guess? Can you guess what it is? You kind of. Okay, what's the derivative? Okay, it's x cubed, right? Because if you take the derivative of x cubed, you'll get back to there. Okay. So sometimes it's kind of a guessing game. You want to keep that in mind, but other times we'll have mechanical processes and rules that basically just you kind of memorize and follow the process. Okay. Right. So let's get in here and take a look at the antiderivative. Derivative, and we should get a nice definition from the book so we don't abuse our ideas of what's going on. So the definition, a function big F is an antiderivative of little f on an open, is it an open interval? So the book is just saying an interval. Okay, so we'll just say on an interval I when the derivative of big F is actually equal to little f for all x on this interval. Okay, so we've kind of already seen an example. Let's look at another example, but with this new notation of big F and everything like that. So we'll say we're given some little f function. So given little f of x equals 4x cubed, we have its antiderivative, big F of x, must equal what? Well, you can guess it's x to the fourth. So why? Because if you take the derivative of big F, you'll end up getting little f, okay, which is basically the definition. Because if you take big F of x and take its derivative, you get little f. So bring down the 4. X, 4 minus 1 is 3. Okay, there's actually more than one antiderivative here, which is kind of weird. So note, in general, this antiderivative you could put a constant on it and it'll still work. Okay, so in general, we note for any constant, given little f of x equals 4x cubed, big F of x can be x to the fourth plus any constant, because, again, I think I'm abusing my commas, because f prime of x in that case, you get the derivative of the x to the fourth is 4x cubed, but the derivative of c is just 0. Okay? So I guess it's kind of like there's an infinite number of answers here. You could have x to the fourth plus 1, x to the fourth plus 2, x to the fourth plus 3. But they're only different in as much as they differ by a constant of some sort. Okay, so you're not going to have like some antiderivative that comes from outer space, right? So when I was first starting, I thought, if I have this function, how do I know there's not some magical UFO antiderivative out there that nobody knows about, or maybe if I just took math for the rest of my life, I would find this mysterious other antiderivative living in the cracks and nookies of mathematics. So it's not the case, though, and we have a theorem which says so. It's used to be Theorem 5.1 in the book, and basically if your big F is an antiderivative of little f on an interval I, and again, this basically just means that the derivative of big F is equal to little f. If that's the case, then we have this bijective statement. So then big G is also an antiderivative of f on I if and only if G is of the form f of x plus c, big F of x plus c for all x in I where c is constant. Okay, so this kind of puts to rest this naive assumption that I had when I was a student that there's some alien antiderivative that may exist on top of the regular antiderivative. Okay, and of course there's a proof in the book. We'll go through it real quick. So going in this direction, in other words, starting with the fact that G is of the form f of x plus c, I want to prove that G is an antiderivative. Okay, so you kind of see that's the direction I'm going. So I assume first that G is of the form f of x plus c, and I also have this initial supposition that f is an antiderivative of f, little f. So we're supposing big F is an antiderivative of little f. In other words, big F prime of x equals little f of x. And I'll just dispense with all the interval stuff. And we also suppose this first half, or I guess the second half in this context, of the if and only if statement. So we're going to suppose that G is of this form. So and G equals big F of x plus c. I think we can just use calculus here. We note then, and I should have wrote g of x, I guess, here. So we note the derivative of g of x, g prime of x, is equal to the derivative with respect to x of this, just by substitution, f of x plus c. That'll equal f prime of x, and then plus 0. And of course, f prime of x is equal to little f of x. And then by the definition of an antiderivative, G is an antiderivative. So hence, I've shown what I'm trying to show. If G is of the form f of x plus c, then G is an antiderivative of f. Okay. So hence, G of x is an antiderivative of little f, of x, basically because g prime of x equals little f of x. And hence, by definition, it works. Okay, the other direction then. So if you didn't notice, that first one was an arrow going backwards. I didn't draw it very well. Okay, so I started with the red part, and then I wanted to prove the green part. In this direction, I'm going to start with the green part, and I want to prove the red part. Okay. So in this first direction, I started with the red part, and I want to prove the green part. I guess color coding things in a weird way. So this time I presume, you had this initial assumption again that f prime equals f of x, but also I want to assume that g is the antiderivative of f. Okay, so here I go. Suppose that f prime of x again is equal to f of x, and now that g is an antiderivative, of f. Okay. In other words, g prime of x is also equal to f of x. Okay. So in this case, what we're going to do is fabricate a new equation. So note this new guy, we'll call h of x, equals g of x minus f of x. And then we consider, I have to go back to the interval I where all this stuff works. I'm going to pick 2 points in I. So pick points A, comma B in this interval I such that, so ST for such that, A is less than B. Okay. We can apply the mean value theorem here because this stuff is going to be differentiable. So from the mean value theorem, hence from the mean value theorem, there will exist a value C such that C is in between A and B, and H prime of C is equal to H of B minus H of A all over B minus A. Okay, what the heck is H prime of C? Okay. Note H prime of x is going to be equal to G prime of x minus F prime of x. And because those things are antiderivatives, it's just going to be F of x minus F of x, which is equal to 0. So that H prime of C thing, if you're willing to believe that is allowable, if you're willing to believe you're allowed to apply the mean value theorem, H prime of C is actually equal to 0. So we can rewrite that expression, let's call it maybe 1. Hence, 1 can be rewritten as 0 equals H of B minus H of A all over B minus A. And then we could solve multiplying both sides by B minus A. And we get H of B minus H of A equaling 0. In other words, H of B equals H of A. So what does that mean? Well, because A and B were arbitrarily chosen, it must be true for any A, B in that interval. And therefore, H of x must be constant on that interval. So because A and B were arbitrarily chosen, H of x is constant on this interval. And so what? Well, we have we have H of x is equal to let's write it as, did I write it as g of x? Yeah, g of x minus f of x, which equals some constant, but then that implies that g of x is basically f of x plus some constant. Okay. Right, so it nails down what the possibilities for g of x can actually be. So g of x has to be of this form, f of x plus some constant. There are other issues that I needed to iron out, I think, before I started talking today. You have to make sure that the mean value theorem actually is applicable here. And if you remember the mean value theorem, it has two criteria that need to be fulfilled. It needs to be continuous on the closed interval, differentiable on the open interval. Clearly, it's going to be differentiable because g of x and f of x are differentiable. If something is continuous, is it therefore differentiable? Well, no. If you remember, you could have something like this, which is not differentiable but continuous there at the cusp. So I'm writing at the top right here. So this was continuous but not differentiable. The idea, the theorem we had back in the day was that if something is differentiable, if diffy, then it's going to end up being continuous. Okay, so if you have these a and b's, if you're picking these a's and b's in the interval, because g of x and f of x are supposed to be differentiable on that interval, they should also be continuous. So you'll have, I believe you'll have then the two criteria for the mean value theorem in place, and then you can apply it. Okay? And it's just because we presumed all this differentiability stuff on these intervals. Okay? I think that's the small and short of it. I wish I had the time and ability to make it more rigorous, but I think I'm going to have to leave it there. Okay, so section 2 then, we want to investigate these things called differential equations. There's a whole class dedicated to this subject. And it has been said that differential equations are the equations, or the language of the universe. Okay, so if you understand differential equations, you can kind of make predictions about anything in the world, right? So anyways, what is a differential equation? A differential equation is going to be an equation involving x, y, and derivatives of y. Okay. An example from later work, you'll have maybe something like y, the second derivative plus the first derivative plus y equals e to the x. And what you're supposed to do with these things, instead of like finding x equals something or something like that, you want to find y equals something. So you're trying to solve for this magical function y. Okay, and that's the game. At this point, you are going to have kind of simple differential equations. Actually, anytime you find an antiderivative, you're doing a differential equation. So an example, y prime equals 9t squared. Okay. So a solution to this differential equation would be y equals, we'll have to find something that, you know, is the antiderivative. So let's try 3t cubed, right? So is the derivative of 3t cubed 9t squared? So yeah, bring down the 3. 3 times 3 is 9. T to the 3 minus 1 is 2. So that thing right there is an antiderivative. And in fact, we could call this a particular solution, because if you remember what we were talking about, the antiderivatives are actually going to look like this for some constant c. So this guy is the general solution. And if you wanted to graph this thing, it would basically be 3t cubed plus c. It's a family of curves, okay, which looks like this in the xy plane. Okay. And then if you want a particular solution, you kind of have to give an initial condition. And our particular solution, of course, is the one that goes through the origin. Okay, so that would be that guy right there. But your solutions to differential equations, the general solution, isn't really just one function. Okay, it's a family of functions. So, okay, so anyways, this process then of finding this antiderivative, we're going to give it some notation. So we denote, and we'll kind of leave this idea of differential equations for a later time. Anyways, we denote the operation of finding this general solution anti-differentiation, or indefinite integration. Definite integration. Okay. And instead of writing out all that business above, where you're writing y prime, and then you go to another line, we can put it all into one sort of answer. So the antiderivative of 9t squared, we're going to use this stretched out s symbol, which is, I think it's actually represents s for sum. Let me rewrite that because it looks like I just masked. This is your first introduction, and I butchered the symbol. Okay, here is okay, that's a little better, I guess. That's the symbol for integration. The 9t squared, the thing inside the integral is going to be called the integrand. And the dt symbol is going to be the variable that you're integrating with respect to. Okay, so this is the variable of integration. And then the integral, this is called indefinite integration. Okay, later we'll have definite integration, but this is equal to then that general solution we got above. So you're going to have to remember to always include that plus c. And if you get stuck with a really mean Calc 1 teacher, they will mark off every time you forget that plus c. Okay. Anyways, plus c is generally called the constant of integration. It's a capital C. Don't forget it, okay? Okay, so basic integral rules then. Section 3 in my notes. Inverse, the derivative and the integral are kind of inverses of each other. And I say kind of because the cancellation equations that you may have learned in pre-calculus for inverse functions, so that, let me over to the side here remind you of the cancellation equations. So if you have f of f inverse of x, you'll end up with x. And if you have f inverse of f of x, you end up with x, right? So here it's kind of like, what am I doing? I'm doing the integral of a derivative of this function f of x, right? Or I guess here, big F of x. So instead of just putting a variable in, it's kind of like you're doing an operation on a function. Okay? You would expect it just to be big F of x, right? But no, whenever you do an integral, you always have to include that plus c. So yeah, it is kind of big F of x, but then you have this plus c thing to deal with. Okay? So, you know, you would think here, maybe it's just big F of x because of the cancellation equation idea, but that's not true because when you do an integral, you can't necessarily tell where that thing came from. You know, it may have been plus 5 on the end of it. Okay. Fortunately, the derivatives do kind of have the cancellation equation property, though. So if you do the derivative of the integral of some function f of x, you are going to just get out f of x. Okay, so basically, if you take the derivative of an integral of some function f of x, then it's kind of like a cancellation equation. Okay. Alrighty then. So they have that inverse property, and I guess for a long time people didn't realize that there were all these cool connections between the derivative and the antiderivative or something. I don't know. You read a book on it. Strogratz has some great books on it that are pretty easy to read. So if you get it like a summer off and you want to nerd out, Strogratz has some books on calculus. Strogratz is a MIT professor. I think he was big into nonlinear dynamics, so he figured out all these kind of analytical ways of dealing with solving nonlinear differential equations, which is just fancy talk for kind of, he figured out a way to kind of use graphs to analyze systems like, lightning bugs flashing in unison and pacemaker cells in your heart and things like that. Really interesting stuff. So if you get a chance over summer, it's not technical at all. And he even has maybe some books on the beginnings of calculus. I think he has one called Infinite Powers or something. I've read them, and they're good read, especially for teachers. I think all teachers should have to be forced to read some of his books. But okay, so there's that. If you want to know that, I used to know all that stuff, and I just forgotten. I used to listen to it every day on my way to work, but now with the pandemic, I stay at home all day long, and I do nothing. Not really. Anyways, right. So other basic rules. We have differentiation. If you know how to do a derivative, you'll know how to do an integral. Okay? And that's kind of the idea behind this next chart that I'm going to give you. You might want to make some cards to memorize. What are they? Note cards or flashcards. There we go. Okay, so you know that the derivative of a constant is 0. So the integral of 0 must be a constant. You see how this works? You know the derivative of a constant times x is equal to just the constant. So therefore, the integral of a constant must be equal to k times x. But you always have to plus c it. Okay? The derivative with respect to x of k times f of x, this is a constant multiple rule. You could pull the constant out of the derivative. And it turns out you do the same thing with integrals. The integral of k times f of x dx is equal to k times the integral of f of x dx. Okay. In general, the first thing you want to do when you do an integral, if it's really complicated, is to pull out the constants. What else? The derivative with respect to x of f of x plus or minus g of x. So the derivative of a sum or difference is equal to the sum of the derivatives, or difference of the derivatives, plus or minus x of g of x. So therefore, also, it turns out the integral of f of x plus or minus g of x, the integral of the sum or difference is equal to the sum or difference of the integrals. Okay. Oh, other rules. We know the power rule. Okay, so what's the power rule for integrals? We'll have x to the n dx. So look at how this works for the derivative. Okay, you bring down the n, so you're multiplying by n. Multiply by n, and then subtract from the exponent. So how does the integral work? Well, it's the inverse kind of operation. So what you're going to kind of go in reverse. So instead of subtracting 1 from the exponent, you're going to add 1 to the exponent. And then instead of multiplying by n, you divide by this new exponent, n plus 1. Okay, so it'll look like this. You'll get add 1 to the old exponent, and then you divide by n plus 1. Okay. So it's x to the n plus 1 plus c. An example, the integral of x to the 5th dx will be x to the 6 all over 6 plus c. Okay. This works for all n values except, so there is a restriction here. N cannot equal -1, right? So you see in the denominator you have n plus 1, so that would be bad news if we had -1 for n. Okay, so we have, so what is that case? What the heck is that case? So we have x to the -1 dx, which you can also write as the integral of 1 over x dx. You can also write dx over x. What is that? Well, does anybody remember what derivative gives you 1 over x? Well, it turned out to be ln of x in general. The ln of absolute value of x is 1 over x. Okay. So the integral of 1 over x is ln of the absolute value of x plus c. Okay. Related to the natural log, then, of course, is the exponential. The natural exponential function. That's an easy derivative. So the integral of e to the x dx is just e to the x. And then, of course, you have your trig derivatives. Sine x dx is, well, geez, what's the derivative side, sorry. So we have the derivative with respect to x of sine x is cosine x. And you should have these guys memorized, right? The derivative with respect to x of cosecant x is negative cosecant x cotan x. The derivative with respect to x of cosine x is negative sine x. Derivative with respect to x of secant x is negative secant x tan x. Derivative with respect to x of tan x is secant squared x, and the derivative with respect to x of cotan x is negative cosecant squared x. So, going in reverse now, the integral of cosine x must be sine x plus c. Integral of cosecant x cotan x dx must be, you got to be careful with the signs because this is not negative. Its antiderivative must be negative. So negative cosecant x plus c. Integral of cosine x dx. Oh, oops, integral of sine x. I already got the cosine. So the integral of, please work, thank you. Stupid pen wasn't working. Integral of sine x dx is equal to, and you gotta be careful here, because the original derivative law is cosine is negative sine, so the reverse of positive sine must be negative cosine x plus c. Integral of secant tan, secant x, whoops, and this should be positive, sorry. Secant x tan x must be dx, must be secant x plus c. The integral of secant squared x dx must be tan x plus c. And then finally, the integral of cosecant squared x dx must equal negative cotan x plus c. Okay, so look at all those derivatives you supposedly are able to do, or sorry, integrals you're supposedly able to do now, just from what you know about derivatives. So hopefully you learned your derivative lessons well, and now this will just be easy, right? Okay, so let me look at that for a second, make sure I got all the stupid signs right. Okay, I think I'm good. Well, let's take a look at some now examples from the book and start doing some integrals. 3x dx. Okay, so first thing you usually want to do is pull out any constants. So you can pull out a 3. And you consider everything in here as kind of multiplied by each other. So it's kind of like you're thinking 3 times x times dx. You want to think of dx as kind of like another variable almost. So you could factor things out of it. Okay, 3 times the integral of x dx. And then it's 3 times x squared divided by 2, right? Plus c. And then make it look pretty, 3x squared over 2 plus c. Okay. So you can always pull, that's a very important technique. So even like if you have 3x plus 3 dx, you can factor a 3 out of there as well. 3 integral, it may not be necessary to do it, but you can do it. Okay. Here's a weird example of factoring something out. It's always kind of freaks people out. 3 all over, I don't know, 3, let's make it 3 sine x dx. Let's not even go there. Let's just save that for the future. I don't want to freak anybody out. All right, so let's look at another example. Integral of 1 over x cubed. Okay. You remember when we took derivatives, we'd always do rewrites so we can use a power rule. That's what you want to do here. So 1 over x cubed is x to the negative 3 dx. And then you're doing the power rule for integrals. So you add 1 to the old exponent. Negative 3 plus 1 is negative 2. And then you divide by that new exponent. Okay. And then you want to pretty it up. So you get negative 1 all over 2x squared plus c. Okay, let's look at another one. So again, it's this idea of rewriting to take advantage of power rules. So here, square root of x is the same as x to the 1/2 dx. When I do fractions, I kind of like to multiply instead of dividing by a new fraction. So it's x to the 1/2 plus 1. 1/2 plus 1 is the same as 1/2 plus 2 halves. 1/2 plus 2 halves is 3 halves. And instead of writing divided by 3 halves, just multiply by the reciprocal of 3 halves. So you multiply by 2/3, and that'll get the job done. Okay. What else? Example 2 sine x dx. So factor out the 2, and then you're just worried about the integral of sine x. So the integral of sine x would be negative cosine x. And then plus c, and then rewrite it. So negative 2 cosine x plus c. Another example. Integral of 3 all over x dx. You can factor out the 3, so you get 3 integral of 1 over x dx. The integral of ln of x, the integral of 1 over x is ln of x. And you always have to include these absolute values. It makes it more powerful. Okay. Let's get another. So this one's kind of weird. The integral of dx, what the heck is that? Well, it's really, it's 1. The integral of 1 dx. And the integral of 1 is just x. Right? Because the derivative of x is 1. Moving on. Okay, so now looking at the integrals of sums. The integral of a sum is equal to the sum of the integrals. So you can rewrite that as x dx plus the integral of 2 dx. Okay, the first guy is x to the 1 plus 1 is 2 all over that exponent. And then plus, you can factor out the 2. And then you have the integral of 1, like before, that's just x, and plus c. Example. Integral of 3x to the 4th minus 5x squared plus x dx. Okay, again, the integral of the sum is the sum of the integrals, if you wish. 3x to the 4th dx minus, and of course we could factor out the constants, 5 integral x squared dx plus integral x dx. So the first guy, if you want to, you could factor out the 3. And then the integral of x to the 4th will be x to the 5th over 5 minus 5 times x to the 3rd over 3. And then plus x squared all over 2. And then plus c. And then clean it up, and then you got it. 3/5 x to the 5th, if you wish, minus 5/3 x cubed, plus 1/2 x squared, if you wish, plus c. And of course, you could also write it as 3x to the 5th over 5 minus 5x cubed over 3 plus x squared over 2, if you wish. Let's look at some trickier one here. Integral of x plus 1 all over the square root of x dx. Okay. The integral of a sum is equal to the sum of the integrals, but something like the integral of a quotient is not equal to the quotient of the integrals. Same for products. It's the same thing as derivatives, right? If you take the derivative of a product, you got to use a product rule. You take the derivative of a quotient, you got to use a quotient rule. Okay, so we're going to have to develop other techniques for dealing with quotients later on, but for now, you try to just turn it into something that's not a quotient. Okay, so the way you could do that is by filleting or butterflying this fraction. So it's the reverse of the common denominator, right? So we'll have x all over the square root of x. Whoops, that should just be x, not x squared. X all over square root of x is x to the 1/2, and then plus 1 all over x to the 1/2. And then we want to rewrite it so we can use power rules. So the integral of x to the 1 minus 1/2 is 1/2 plus x to the negative 1/2 dx. And then add 1 to the exponent. So 1/2 plus 1 is 1/2 plus 2/2, which is 3/2, and then divide by 3/2, which is the same as multiplying by the reciprocal, 2/3. And then plus x to the negative 1/2 plus 1 is negative 1/2 plus 2/2, which is 1/2. And then divided by 1/2, the same as multiplying by the reciprocal, which is 2. And then plus c. Okay. Another one. Just doing a ton of examples here. Sine x all over cosine squared x dx. Again, I don't really know how to deal with a quotient at this point, so one trick is to just rewrite everything, right? So I'll have sine x over cosine x times 1 over cosine x dx. And then I could use my rules for trig identities. Sine over cosine is the same as tan. And then 1 over cosine is secant. And then I know that derivative. Tan secant is a derivative of secant. So this would just be secant x plus c. What else? Let's look at this thing. Integral of t squared plus 1 squared dt. Again, I need to rewrite it so I could use a power rule on it. You can't basically, I mean, you can't like go t squared plus 1 to the 3rd over 3. That would be insane. It's just like you got junk inside there. It's like I need a chain rule or something. The reverse chain rule, which I don't know how to do. So what I'm going to do then is FOIL. So t to the 4th plus 2t squared plus 1 dt. And then I could use power rule. So use only the stuff that you know how to do. Don't, in general, don't make up new stuff unless you're sure it always works. I mean, certainly experiment if you get a chance. 2t cubed over 3 plus t plus c. I'll dispense with chopping up the integral and just go straight to the point. Oh boy, is that about it? Oh, let's look at this one other one. Cube root of x times x minus 4 dx. Okay, so here again we have a product of two things, and you know, naively you may think the integral of a product is the product of the integrals, but I already said no, it's not. You would need some sort of product rule for integrals, which we don't have yet. So you have to turn it into something you know how to do. And the only thing I really know how to do well is that stupid power rule. So I'm going to distribute, okay, x to the 1/3 plus 1 is x to the 1/3 plus 3/3, which is 4/3, and then minus 4x to the 1/3. Okay. Cube root of x is x to the 1/3. And now it's in a nice form where I can do something I know how to do. Okay. Very important to know your limitations. 4/3 plus 3/3 is 7/3. Divided by 7/3 is the same as multiplying by 3/7. Minus 4 times x to the, and I leave a little space between the 4 and the x. 1/3 plus 3/3 is 4/3. And then I have to multiply by 3/4. And don't forget your constant. Okay. So I have 3/7 x to the 7/3 minus 3x to the 4/3 plus our integration constant. Okay, way back here, I talked about general versus particular solutions. So in general, when you do an antiderivative, you're going to get this plus c thing. Okay. If you have an initial condition, you can figure out where you are. Okay, kind of the particular solution in the family of curves. Okay, so that's what we kind of need to talk about here. Section 4, initial conditions. And also particular solutions. Okay, so example, find the general solution and then a particular solution. So find the general solution of this differential equation, f prime of x equals e to the x. Then find a particular solution given f of 0 equals 3. Okay. Okay. So the first thing we do is get the general solution of f prime of x. Okay, so f of x will end up equaling the integral of f prime of x, which is e to the x, dx. And of course, when you integrate a derivative, you're going to have that plus c thing popping out. Okay, so we have a general solution here, not a particular solution. If you wanted to think of that as a family of curves, if you were to graph that, right, x, it would look like a bunch of these, right? That represents the family of e to the x plus c. We want a particular one, okay? And we can find the particular one given f of 0 equals 3. So 0, 3 is going to be right here. We're going to be looking for this particular solution that goes through this curve, or goes through that point, excuse me. Okay, okay. So how do I do that? Well, you're going to just plug in 0 and 3 into the thing, into this general solution. Okay. So let's go to the general solution. The general solution is f of x equals e to the x plus c. And I'm plugging in 0. F of 0 is 3. And then I have e to the 0 plus c. E to the 0 is just 1. So I have 3 equals 1 plus c. So c will equal 2. And then that tells us our particular solution. So this is the general. And then the particular guy is going to be big F of x equals e to the x plus 2. Okay, so you'll do this a lot, especially when you're dealing in physics. You'll need some initial conditions, and differential equations in general, you need to worry about initial conditions. Let's look at this example with vertical motion. And what they're saying is they're throwing this ball upwards with an initial velocity of 64 feet per second, and they're standing on top of some building, which is 80 feet tall. Okay. And you're throwing this ball, and it's coming back down. Okay, okay, so they told us the initial which they usually give the variable v sub 0. That's my cursive v. And in this case, it's 64 feet per second. They're also going to tell you the initial height. Okay, so the initial height is, usually they use s sub 0, so that's my cursive s. That equals 80 feet per second. Part A of the question, they want you to find the position function s as a function of time t. So find s of t, which will give you the position of the projectile. Okay. So I guess we need one other bit of information, and that's this the gravitational constant, right? So in our case, we're going to use g equaling negative 32 feet per second squared. Okay. And in particular, what this thing is the acceleration. And the acceleration is basically the second derivative of the position. So the first derivative, so note, I guess, if you have the position function, the first derivative is going to be the velocity, and then the second derivative is going to be the acceleration. And here we're saying that the acceleration is negative 32. Okay, so what we're going to do is kind of work our way back up to the position function from the acceleration function. Okay, so we note that the velocity function, in other words, s prime of t, which equals the velocity, will be the integral of the acceleration function, a of t dt, which in this case is negative 32 dt. So the integral of negative 32, you can factor out the negative 32 if you want, and then the integral of 1 dt is just t, and then plus c. Yeah, butchered that. Okay. Then we could use our initial velocity to figure out what c is. Okay, so we use initial conditions to figure out the constants. So our initial velocity was 64. Okay. So s prime of 0, which of course is v of 0, is 64. So substituting in v of 0, we'll have maybe noting v of t again, rewriting that so it's a little more clear, negative 32 t plus c. V of 0 is 64, so that'll be negative 32 times 0, just substituting in 0 for t, plus c. So c must equal 64, and we can rewrite our velocity equation as negative 32t plus 64. Okay. Then we need to get our position function, so s of t, which equals the integral of the velocity function dt, which equals the integral of negative 32t plus 64. And you're going to end up with another constant, but we know the initial height, so we'll be able to solve for it. Okay, so this is equal to negative 32t squared over 2 plus 64t plus c. And we can simplify that, of course, and rewrite it. And finally, we have our position function, kind of, negative 16t squared plus 64t plus c. I need to use the initial position, which was 80 feet. S of 0 is 80, and that will allow me to solve for this next constant. So I'll have 80 equals, and I plug in 0 wherever I see t. And I get c equals 80. So at the end of the day, hence the position function s of t will be negative 16t squared plus, I think it was 64t plus 80. Okay. Okay, usually in physics, they just give this formula to you. In general, they give you S of t. So in physics, they give you S of t equals 1/2 g t squared plus v sub 0 t plus s sub 0. Okay, so if you're wondering where, we can now derive it, just given the gravity and the initial conditions, we can find a formula to predict the trajectory of a projectile. Okay, it's pretty sweet. Let's leave it at that. I'm sure the book has follow-up questions for that formula, but we'll leave it there and leave that up to you. And thank you for watching, and I hope you have a good day. All right, bye-bye.